All right, you ready to take a look at these problems here, guys? Here they are. We got our equation, right? Our equation is here. The drag is 1/2 times rho. What was that rho? The air density. Velocity squared. Don't forget the square. What is CD? Coefficient of drag. And then the area of reference, the aerodynamic area of this, whatever it is that we're launching or moving or flying through the air we want to find the drag on for. All right, so in this problem, Brendan's launching his model rocket. He launches it at sea level, so this tells us what our atmospheric density is going to be, right? The initial velocity is 155. We want to find the drag. So, what number did we plug in? What number did we plug in for P? Sorry? Cool. Same number we used before. What's our velocity? Good. 155 squared. Okay. What's my drag coefficient? Because we're using the rocket, right? 0.75. And how about my area reference? My surface area? We found it yesterday, right, guys? Sure. 0.00490, because we used the 0.079 as our diameter, right? Multiplied it by 5, by half, 0.5, right? Because we wanted half the diameter. Times it by pi, right? Pi r squared. Making sure you guys are with me here. 0.00490. Okay, so what do we get? D is what? Not 68,000? Okay. Does anybody have a number for me? I didn't actually do these. I figured y'all this would be super easy. 54.1? 54.1? Okay, that sounds about right to me. 54.1 what? Newtons. Again, that's number 1. Okay? The only difficulty with these was that I was making you go back to the actual graphs, the charts that I gave you, right? I didn't just give you numbers. Because again, that's how scientists work, right? You have to actually find what you're looking for. Okay, so Joyce wants to one-up Brendan, and she has her rocket that she launches, and we want to measure it when it reaches 2,000 meters. Why did I tell you that? It's a different atmospheric density, right? So you'd have to look on the chart to find what that atmospheric density is. Density of air, right? Oops, wrong one. Here we go. Helps if I put the marker down. And again, this table is in English units, right? So feet per second squared, pounds per inches squared. So you don't want to use that table. You want to move down here to SI units, which is what we use, right? And at 2,000 meters above sea level, our absolute pressure is here. But remember, sorry, not pressure, my apologies. Density is what we want, right? And again, it's 10 to the negative 1, the units are, right? So it's 1.007. Why they don't just make it that number, I don't know, but there must be some standard reason why they do that. Yeah, that's the right here. That symbol is that rho. Okay, so that's what I would use there. Velocity we gave you, right, in the problem. Our drag coefficient's the same, and the area of reference is the same. And I plug in my numbers. How about for number 3? What's different there? Okay, so we're changing from a rocket to a car, right? And Nels has his BMW E33 series. Very slick car, right? Now, if you go, because again, I tell you how fast he's going, and we want to find the drag on the car. Notice I gave you just height and width for his car, because we're basically going to just look at his car as a rectangle, right? The front of his car as a rectangle. Now, that doesn't exactly work for this aerodynamic drag, but we're gonna just make it easy and do that. Okay, exactly. We'll pretend he's got a nice rectangular car. It's very strange. Okay? So, what else do we need? We assume he's driving on the surface of the Earth, right? He's not like flying through the air at 3,000 meters. Okay? So we assume that we're at 0, so we can still use that 1.225. What else do you need to know? The drag coefficient, yeah, of the car. And again, that was on the charts that I gave you guys, right? Drag coefficient of the car. Oops. Keep forgetting to have a marker in my hand. Do we see it? What was our number for that one? There we go. The BMW E333 series, so 0.33 is the drag coefficient on that car. You plug it in. Sir?
Wait, how did you know the P again?
How did you know the P? Yeah. Where is he driving? Like what altitude is he driving? Yeah, it doesn't say, so we can probably assume it's just on the ground, right? Just like at 0. No, I hear you. I guess I should have given you something there. But if I don't give you any information, I would just assume it to be at sea level, sure. Yeah. He's driving on the beach with the sunset going down with that special somebody in the seat next to him. Yeah, it's beautiful. Yeah. Going 85 miles an hour. We didn't talk about that, but. We cool? All right, last problem. And again, I'm just running through these. I'll put the answers up for you, but again, I think that you all are able to plug numbers into calculators, so that's why I'm not actually going through the different pieces. All right, so not to be outdone, Neha, of course, has a much nicer car, Tesla Model 3. I can definitely take one of those guys. And she's traveling 125 miles per hour, right? 55.9 meters per second. And we want to know, again, what's the drag? So you'd have to go back to our chart to find the drag on her Tesla, which was lower, if I remember. Yes, here we go. 0.23 is her drag coefficient. A little more aerodynamic, a little more better materials that are less sticky. Are we cool? And again, we're assuming that she just drives at sea level. I didn't give you information there, but that's what I would assume. Does this make sense, my friends? I think you're starting to see, again, these three pieces. The surface area, the drag coefficient, and the altitude, the air density. These three pieces are what make the huge difference in how much drag you have present. Sir?
So, the first one, for finding the P, we use temperature.
So you could, right, because again, one of them we talked about the temperature being different, right? Yeah. At 15 degrees. So there was two different pieces that I gave you since we're at sea level. There was one of the charts, I think it was this one, that had at sea level different densities based upon temperature. Yeah. So you could have used, which again, that's what they have as 1.225. That's what we've been using. Yeah. Okay. But it would change. Notice it doesn't change much, right? It's a little bit of change, but it is there. If you look at this chart compared to the other chart, altitude affects it much more. Because the numbers change much more significantly there. Come on in. Does that make sense? All right. Where I want to go for, Grace, you don't want lunch, do you? What I want to go with today is this simple little piece about terminal velocity. So go back to our discussions that we've had in the past about terminal velocity. Do you remember like what it is? Can you give me like a general definition of what terminal velocity means? Sir? Beautiful. So I'm falling, and I always think about a skydiver when I'm thinking about terminal velocity, right? You jump out of a plane, and you start falling, and you're speeding up, right? You're accelerating as the earth pulls you down. As you do that, you have drag, right? the air pushing up against you as the earth is pulling you down. Well, eventually, those two forces, if you fall long enough, will equal out, right? In other words, as I said here, the drag would equal your weight because, of course, force of gravity is dependent on your weight, right? And if those two things are equal, you are now at terminal velocity, meaning you are no longer speeding up. Are you still falling? Yeah. Do you still have velocity? Yeah. I mean, you're still moving, but you're just no longer accelerating. Does that make sense? Again, most of the things you and I deal with, we don't achieve terminal velocity with. Okay? At least most, I don't know. Maybe you do something else that I don't know about. But that's not usually something that's in our world. But if something is falling for a long enough distance, it will. Absolutely. Based on what? Based on how you calculate the drag, right? Which would then put all three of these things into it. The density of the air, the area, this is the biggest one, the area that they are overtaking, and of course the drag coefficient. Again, if I go back to skydiving, think about the position that the folks normally are, right? Kind of that spread eagle position, right? And they can fly like that for a good long period of time. What happens if they do this? They start going super fast, right? Because now they've significantly decreased that reference area, that surface area that the drag is acting on, and so therefore they'll have a faster velocity. Does that make sense? By tucking into that nice tight bullet shape, they've decreased the drag, so their velocity will increase. Can you still get terminal velocity in this shape? Sure, of course. Again, when their weight equals the amount of drag that's present. Does that make sense? So what if I wanted to know the terminal velocity of our rocket? Does that make sense? So in other words, I'm trying to find velocity instead of just me giving you a number like we did yesterday, right? So, do I know what the drag would be? What number would the drag be? The weight. Okay, so loaded, how much did your rockets weigh? And again, we don't have all the components, but what did you get a number for in kilograms? 1.85? Okay. How about we add another half a kilogram for the parachute and the rocket motor? I don't know for sure how much those things weigh, but we'll put that on there. So I put another, so that would be 2.35 kilograms. Okay? But is that weight? Kilograms is a measure of weight or mass? It's mass. How do I find weight? By gravitational acceleration, right? Times 9.8 meters per second squared. Okay. So what does that give me? Should be close to 23.5, 22 and a half, somewhere around there. 23.03. Okay. And again, we're in newtons. So we're saying that that is our drag force. Sir? So pounds are an SI, are not an SI unit, and pounds actually are a measure of force. They aren't a measure of mass. Like it's its own unit. Like it doesn't necessarily break apart. We've just kind of, how about it's a layman's kind of unit? Like it doesn't necessarily, as far as I know, I could be wrong about that. I've never actually looked into that piece. But they do mean, when they use pounds, usually they're talking about weight, not about mass. Okay, so this number is our drag, right? So weight, you have to deal with gravity. It depends on how much gravitational acceleration you have. For example, I weigh 220 pounds here on this Earth. If I go to the moon and step on a scale, I'm going to weigh significantly. I'm going to weigh like 40 pounds. My mass is the same. Nothing has changed here. I still have the same amount of matter. It's just there's less gravity. So therefore, does that make sense? Okay, so can we calculate this velocity? Can I switch this equation around to get v by itself? Can I do that first before we go anywhere else? I'll put this over here, 23.03 newtons. Because again, I prefer to change the equation around first before I plug in numbers. If you prefer the other way, that's fine. But I think it's easier to do. Are you comfortable? All of these are just multiplying times v squared. So I can just divide them all out. So therefore, my velocity is going to be equal to the square root of my drag over 0.5 times rho times my coefficient of drag times my area of reference. We cool? And we can plug in our numbers, right? For our rocket, we said our drag was going to be 23.03. 0.5 times, excuse me, what's my rho? We'll take that same that we've been using. What's my coefficient of drag? 0.75. What's my reference area? 0.0049. Again, we're still talking about our rocket here. So we're multiplying all those, dividing 23.03 by that, and then taking our square root. So can somebody give me a velocity? Pop it in. What? 0.75, yep, that's my CD, my drag coefficient. And 0.0049. 101. Okay. Let's see if anybody's got a different answer than that. Yeah, mine didn't come out right. 101.15? Okay, beautiful. What would my units be here, friends? Meters per second. Excellent. And that's pretty darn fast, right? Let's see. I don't pop it in real quick into my handy units app. Let's see what we get here. It would be nice, wouldn't it? 101.15. Yeah. 220, a little over 225 miles an hour. I mean, so that thing is moving, right? Again, this is terminal velocity. This would be the point when the mass and the acceleration of the Earth, when the force of the acceleration of Earth equal out. Are we cool? What if I wanted to find the terminal velocity when the rocket is with the parachute? Does that make sense? So if the parachute is now opened, our main chute, because this kind of has two little pieces on it. There's one little tiny chute that kind of helps keep it stable as it begins its fall, and then a large parachute that comes out that slows it down significantly. So I'm telling you that that parachute has a diameter of 1.15 meters. We cool? What would change in this from what we just did? The area, right? Are you comfortable you'd have to find the area again? How do I do that again? Remind me, how do I find area? Well, what shape is the parachute? A circle. Cool. How do I find the area of a circle? Pi r squared. Okay? But of course, I've given you diameter, so you got to divide it by 2. Okay? So what would this be? Can somebody calculate that for me? What would my area be of this parachute if I have a 1.15 diameter meter parachute? Giving your fingers a workout on the calculator today. 1.03? 1.04? Okay, 1.04. And again, that would be square meters. We cool? All right. Again, we said our drag was 23.03. What was our rho? 1.225. What was our coefficient of drag? 0.75. And again, I'm trying to find V again. So we'll use, again, that same equation. Oops, not sure what that was. That V is drag over all the other pieces and take the square root.
Where did you get the 3.03 from?
This, we got it from calculating the weight of the rocket. We took the mass and multiplied it by the gravitational acceleration. We weighed it on the scale. Yep. Are you with me, my friends? All right? Can you pop this in? And let's see what the velocity looks like. Again, this is terminal velocity of your rocket with the parachute open. And we'll do some comparisons to see how that compares to without a parachute. .94. Check to make sure. So let me still calculating. Not that I don't trust these two over here, but got to watch out. They've been up late with those babies, you know. Sometimes it affects the brains. .94? Yeah? I see at least one more head shake. Looking for maybe one more. Yeah? Good? And again, my units are what? Meters per second. So my question to you is, would you rather have your rocket hit the ground at 6.94 meters per second or 101 meters per second? It would be more fun. It may be detrimental to the rocket. All right? That's a huge difference, right? A humongous difference. Just do me a favor. Do 101 divided by 7. I'm just curious. Because I can't do that math quick enough in my head. So yeah, almost 15 times less velocity. Which is pretty impressive, right? And that's not even a humongous parachute, right? That's just a meter, just over a meter, which is impressive. You see now, though, but if you think about, like, if you watch the rockets that launch, and when they actually kind of recapture, boy, even though space shuttle, that's getting old. You guys have never actually seen the space shuttle launch. It's too old for you. Maybe you've seen it on video before. But they would actually recover the boosters. Do you all know what I mean? I see some blank faces, and that's a sad thing for me. I used to have posters of the space shuttle up in my room. Yes, that's how nerdy I was. So here is what it looks like. All right? So, when it launched, these guys were what provided the main force. These were the booster rockets, right? They provided the most of the force for launch. This big orange thing, you know what that was? It's just fuel. Like that's all just liquid oxygen, liquid hydrogen that they put together to literally blast it out the back end. Remember when we did the little micromole rockets? You know, where you all mixed the oxygen and hydrogen and we shot them with a little sparker? Like that's the same reaction. I mean, slightly larger scale. Tiny bit. So these things would actually, after they got up a certain altitude and they ran out of fuel, they would jettison those off. And they would come back under parachute. Booster parachute. And it's tough to have any sort of reference, but are you comfortable those are humongous parachutes? Why so big? A lot of drag because it's going pretty fast, right? And what else? It's really heavy. The weight, even though it doesn't have any fuel in it, it's still a very heavy piece. So you need a much larger surface area so that it can hit the water. These landed in the ocean, like this shows very nicely. Because they could recover, they could reuse these. That was the whole big thing about the space shuttle. It wasn't just you launch it once and it's done. That's what like SpaceX is doing, right? That they actually have rockets that they actually land them on a platform, which I think is fairly cool, actually, to be able to control that. It's a great. I honestly have no idea. We can look it up. I'm sure it's out there. Quick. Size of space shuttle booster rocket parachute. Over a million pounds. Yeah. Yeah, they are big, almost 150 feet tall. No quick, easy answer for you.
Gotta be at least like 50 feet wide.
Yeah, easily. They were humongous. We could find it. We could find it. All right. So, does this make sense? Let me go back to where we were here. The main piece of what I want you to understand, no difference in the equation, right, guys? No change in that equation. The aerodynamic drag is still the same. The only new thing I'm teaching you today is simply this. If you want to find terminal velocity, the drag now equals the weight. Make sense? And if you know the mass, the weight of your rocket, or whatever it is you're firing, you can determine its drag.